Hello, my name is Eduardo. Let's see. I work doing OCaml for a couple of years, and I'm mostly known from my Twitch stream and saying stuff on Twitter. So yeah, the talk is called Easy GADTs by Repeating Yourself, but I want to go first on the easy GADT side. Personally, I'm kind of upset with GADTs because almost always when we start to use them, the code gets really, really messy, okay? And so I used to work on a blockchain. It's called Tezos. We had a full-fledged interpreter using GADTs, and it was so much fun. By fun, I don't mean in a good way. So yeah, historically, it's ended up being messy, not principled, full of hacks. So here I'm going to start by giving an overview on GADTs. And then by the end, I should be presenting a general technique on how to make GADTs even messier. But at least, they get more fun. And so you should probably not use what I'm going to be saying today in production. It's the opposite of what some talks here are presenting. It's not driven by real-world use cases. It's just driven by, we having fun. So first, what are GADTs? GADT stands for Generalized Algebraic Data Types, okay? The generalized side is a mess, so let's focus on the implications of that, which is GADTs are essentially existential types plus equalities. The first thing that we need to understand is what in hell is an existential? Existentials are not They are not as common of a feature as universals, so like generics, but they are kind of the same thing but reversed. For existentials, we have existentials whenever we have a variable like this, and this variable is not bound anywhere. You can see that, or there is no parameter. So this variable is unknown on any. Whenever you have a value of type show, you don't know what this variable is, but you do know some stuff. You do know that this A, and this A here are the same. So you can do stuff with it, but without knowing it. This is similar to generics, again, as I mentioned, but slightly different. So the way that you could use an existential here, and we're using GADTs to introduce the existentials. There is some other ways, but creating a value of type show is pretty standard. So I can just create the ADT. And the main thing here is that this A on this ADT is going to be an int, but it could be a string, a bool, whatever you want. And then we are using it to print the show package. We are converting it to a string. We are doing show. The main thing that is not exactly standard on this function is what is the type of content inside of this function. We don't know what this EX is. It's a show, but it could be anything. And in fact, it's actually a dollar symbol EX show A. So historically, that's a good type. We know what it does and what it doesn't. This type is unknown. Essentially, whenever you see a dollar symbol, you can know this was introduced by a pattern matching. So this pattern matching here. And the main thing that it does, it represents that hidden variable that was present on the declaration. So this variable here, you can see the A, it's this. And you cannot do much stuff with this except whatever it's defined on the specification. So here, we know that content is EX show A, and the show function on the record also takes an EX show A. So I can use this content on that function, and I can call it. This works kind of okay, but the implications are very strong. A common one is that this content cannot be returned. So this is an error message that most OCaml developers are going to see at some point, and they are going to get very I don't know what is going on, I'm just running, which is essentially a type constructor something would escape its scope. What it means is essentially that if you try to write the signature of this function, so if we're trying to find what A is, it's not going to work because we don't know. From looking at show, we don't know what A is. We just know that, it's EX show A, but without full-fledged dependent types, you cannot do it. You can also do existentials using first-class modules. You can see it here. The thing about existentials using first-class modules is that, at least in my opinion, it generates better error messages. Because instead of saying ex show a, it's going to show like the t of the module. But again, the same problem would happen. Let's say we were trying to return content. If you try to do content here, you would not know because there is no s on the signature. There is just show. So that's kind of all that there is to existentials. They, like generics, they're kind of useful, but in general, they are less useful. So as you get fancier and fancier features, they tend to become less useful, except by the case that you cannot do at all without them. Here, we're mostly not going to be focusing on existentials, but on the other side of GADTs, which are equalities. Okay? Equalities are kind of simple. Essentially, what they allow you to do is say that two types are equal. But now, the mechanisms and the way that they work, it's not so standard. Essentially, on the definition of the equality, like here, you can apply a constraint on the type constructors. On the parameters of the type constructor. This constraint is going to be like x and x. And essentially, here we're just saying that they are the same type. So whatever goes here must also goes here. So while it looks like a very generic type constructor, I'm not even looking at the parameters. It's not that generic. It's pretty weak. And this leads to some nice implications. It's also why I'm calling it an equality. The first implication here is that you cannot construct a riffle of type string and int, for example. You can do string and string. And in fact, you can do it for any case that the left side and the right side are the same. But you are never going to have something of type string and int. Keep that in mind. You're never going to have something of two types that are not equal. Because of that, we can assume some stuff, and we can use it to do some operations. And this is supported by the OCaml compiler. The main thing that we can do is we can transform something of type A to type B by using an equality. Essentially here, if we have an equality, then both sides are equal. And by pattern matching on it, the compiler works. The compiler is going to allow you to cast it. The major way that I recommend you all to read this is for all A and B, if you give me an equality stating that A is equal to B, and then you give me something of type A, I can convert it to type B. This is actually kind of a weak version. There is a more general function that equality needs to satisfy, which is this. The problem is that then we need to get into functors, and whenever we go there, it's not as fun. But the idea is that this is slightly more powerful, not because only I can convert A to B, but because I can convert A of T to B of T. So like, if I have a list of A, I can convert to a list of B. If I have an option of A, I can convert to an option of B. A and B are equal in all the context. This is very powerful. We call this, you can think about this as Leibniz equality, Leibniz. And you can also describe it as using first-class modules. It's just that it gets so much messier. And the main thing about GADTs here, when comparing them to first-class modules, is that you should keep in mind that GADTs are so much nicer to use than first-class modules. You can use first-class modules. In general, they are even more powerful, I would say. But GADTs are so much more convenient. And here is an example of a thing that you can do with GADTs. Remember, because I said that you can never have something of two types that are different. I can never create a riffle, but I can assume this equality to exist. So if I do string and int, so this is going to be of type string and int, what happens when I match on it? Well, it cannot be riffle. In fact, it cannot be anything. So we have what we call a refutation. We refuted this case. And because, well, there is no case, this works for any type. And this also leads to like a nice interpretation of types, a way of seeing of these types, which is, what is this A here? Like, this function returns anything. There is no function that returns anything because, otherwise we would not have soundness and all the cool properties of doing OCaml. So what happens is, whenever you see a function of this shape, that it just returns a random A, that it's not constrained anywhere, this random A this function cannot return. And so you have three options in OCaml. Either this function is going to enter in an infinite loop, which is not the case here. Either the function is going to raise an exception, also not the case, or you cannot call this function. So in OCaml, there is no way of calling this function, which means, we refuted the case. We know that it's never going to get there. We do it by using this dot. Not going to say it's the best syntax. It's a weird syntax, but it kind of works and it tells the story. The other thing that you can do is you can get kind of fancier. And remember, the equality itself is just a value. You can put it on a pair. You can put it on an ADT. The implications of the equality is nice, but equality, just a normal value. So here, what I'm doing is I have a function that either takes an equality, saying that a is equal to int, or either takes an equality, saying that a is equal to bool. The conclusion of this is that either a is going to be int, or a is going to be bool. This looks like a generic type, but it's not. It only works for int or bool. And by looking at the value, by pattern matching on the tag, and on the equality, I can actually convert a. Remember, content is of type a. I can convert content to int or bool. This is something that can get really fancy. Okay, so here it's where like most of the magic is gonna happen. And some of you guys here are used to do TypeScript, and this is the kind of stuff that you can do on TypeScript, which is not to say that it's a good thing, but it's really fun. So what are people actually using GADTs for? So now, we kind of understand there are existentials and there are equalities. We're mostly using them for small equations, for saying that like some small properties. So here in this case, it's a very classical example. Either this parameter is int or bool, or a list of int or bool of a list, or int or bool of a list. And yeah, it's kind of recursive. But that's kind of the main idea. There is also another nice property about this. By knowing the value, so if I know which ADT it is, I know what is the type. And vice versa. If I know the type here, I also know which ADT it is. So on the type level and the term level, we have the same thing. This is, a classical function that we can do. This function works for all the supported types. And again, for all ATY, A to string. Again, this A looks generic, but it only works for those cases. And again, same conversion. We see content here, it's going to be an int. Here, it's going to be a bool. Here, it's going to be a list. But you can see that we have, the tag indicating what is the type of the elements. And I can just serialize the elements and concatenate. And then I can call it like this. So you do show to int, to list, to bool. And this function works for both of them. Essentially, here we're adding like a runtime for types. OCaml does not have a runtime for types, so whenever you compile OCaml, if you look at the binary, if you look at JS, there is no types there. So you cannot do like if type off. But this is what if type off is doing under the hood. So in something like JavaScript, you have the type off. And the reason why if type off works is because there is this tag implicitly on every value. There is no tag in OCaml. But I want to comment that this works, but it's not very principled. Here it's working for a very, very specific task. What if we want to make it more general? Like, we're just relying on some small relations between this and this, but these relations are limited and only on the definition. But let's imagine the goal, the dream, maybe the future dependent types. We all in this room probably love them. I know that most people were not even introduced. But I'm going to try to give a brief introduction of dependent types, why you should be excited for them, what they do. The main idea of dependent types is that you're going to have a type constructor, and it's going to look on a value, and it's going to return a different type based on that. That's it. So here, of course, this is not valid OCaml. We are, just hand-waving syntax. Here, I'm pattern matching on the tag. Imagine that a type constructor acts like a function. So I'm pattern matching on the tag. If it is int, I return int. If it is bool, I return bool. If it is a list, I return and recurse. The fun thing about this is that there is no more mess here. This is simple, okay? But this doesn't work. And even if it did, that's how you could use it. So this is valid syntax for OCaml, not valid semantics. You can see that the tag appears here on the type. And that is nice, but it doesn't work because this is not defined. In OCaml, like a value variable cannot appear on the type level, which is the main limitation. This is not going to work. In principle, we could make it work, but then we're going to need to do a lot of fun stuff. For me, the reason why this is so much better than the previous GADT solution is that I don't need to think about relations. I just have, I know how to do pattern matching. Everyone here knows how to do pattern matching. I just want to do the pattern matching and say, if it is X case, it's going to be that type, otherwise it's going to be that other one. And I feel like every time that I talk to someone coming to OCaml from something like TypeScript, this is actually something that a lot of times they want to do. Sadly, they can't because by default the language is not that expressive. But yeah, I want you to imagine that this example here, it's the same as this. So at the end of the day, I just want to do a pattern matching on the annotations. Better than that would be able to abstract the pattern matching away. But here we want to do the pattern matching on annotations at least. Again, doesn't work. That's not valid OCaml. So here we get to the second step of the talk, which is repeating yourself, duplication. Remember that I mentioned the main problem is that we cannot have a value on the type level, and actually vice versa. So instead of having a value on the type level, or a type on the term level, what I'm going to be proposing is that we're going to have something similar. We're going to have the two objects, one on the type level, one on the term level, and they're going to be the same, one-to-one mapping. But whenever I want to do the pattern matching on the type level, I use the type one. Whenever I want to do the pattern matching on the term level, I use the term one. So I don't need to actually cross this barrier. I'm just using, plain old OCaml. The problem of that is that now you need two objects. You need one on the term level, one on the type level, and sometimes you also need a package to bind them together, which gets really messy. But that's what we are doing today. So let's first start with our definition of type. This looks similar to the original one. Those are empty variants. They're actually relevant. We're not looking at those. But the main idea is that if I know the type of TY, I know the constructor, and if I know the constructor, I know the type. It's a one-to-one mapping. They have the same properties. So if it is tint on the term level, it's going to be tint on the type level, tbool, tlist, and recursively. If I know it's like tint, tlist, list, I know that it's going to be a tlist, tint, because it's reversing OCaml, also not prime OCaml syntax here. And so let's see how we could now define our function that we couldn't previously. So this function right here, so type. How we can define it now? Well, the main idea was if it is this, it goes to this. If it is this, it goes to this, and so on. We're still doing the same thing. If it is tint, it goes to int. If it is tbool, it goes to bool. If it is tlist, it goes to, it recurses and then takes the return of the recursion and put it here. The main difference is that we have an additional parameter. This is our return. So we are still thinking about relations, but think about it. A function is a specific kind of relation. It's not a general relation. It's a relation that, like, for every input, I get one output. And so that's kind of what we're doing. And we can even do the recursion here, which is generally a problem. But yeah. And then we can use it. Let's not look at the signature for one second. We can use it by simply adding those additional pattern matchings here. So there is this one, and this one. And this code type checks, okay? And it's doing exactly the same thing that the original demo was doing, but in a worse way. And we're going to get worse before getting better. Essentially, what we are doing here is we're introducing this new parameter, okay? I want to explain what this new parameter is doing and how you can read it. If you do some mental transformation, it gets easier. Remember, this is the return, okay? This is the return of the function. So this code, it's for any tag, the TI here, which again, tag here, it's the same thing. It's just that it's on different levels. We duplicated. And here we're saying that the parameter is the content. A good way, which sadly does not work in OCaml, like most things here, is that this type is the same as this. So the content is equal to the toType of the tag. Because we cannot do this directly, we cannot put toType tag here. I need to bind it on a variable, so I make a variable that's the only reason why the variable exists. And I use it as an intermediary through this index. Again, just flip it. This content is the return, so content is equal to type W of tag. This works in all the cases. You can play later. And another interesting thing is that those witnesses, we call those values that are not super relevant on the term level. We call them witnesses because they are just there for like satisfying the type checker. They're not doing anything properly. They are not relevant. Like, look at this pattern matching. This is the same as unit. There is no extraction here, no extraction here. And here, there is an extraction, but remember, because all the other cases are irrelevant, so I'm also not using this here. I'm just satisfying the type checker. This is really good, because if we had some optimizations, maybe on F lambda 2, maybe a propositional mode, this could be 100% eliminated from the runtime. And if you try something like this in Agda, Coq, or Idris, you're going to get this behavior where this is not going to be on the runtime. So this is only satisfying the type checker. I'm not sure like what assembly right now looks like. It's for this and this, it's probably going to not be there. But I think for this, it's still extracting. Sadly, sometimes the OCaml typers, the OCaml compiler is not very smart. And yeah, this just works. I'm going to make the arguments on why later. But notice the thing. Now we have an additional parameter. The parameter carries the witness and whatnot, as I mentioned. But we have a problem. How do we call this function? Before, calling the function was a matter of like provide the tag, provide the content. That's going to work. Now it's not. We are not, where we're going, it's not going to look that good. So we also need to have a way of creating this witness. Remember that I mentioned duplication. That's the point of the talk. We're going to have one-to-one mappings and whatnot. In the same way that this was a one-to-one mapping, this one is also a one-to-one mapping. From tint, it goes to wtint, tbool, wtbool. Notice that I'm just making the value based on this. And so, but there is a problem, which is for reasons we need to have an intermediary type to bind them together. So we know the return is existential. This is all the existentials that we're using on the talk. So we don't know what this R is, but we do know the tag. Notice that tag is actually exposed on the constructor here, but not R. So the main idea is that this function is going to return this, and you're going to extract it later, which now that we have everything, so we have all the parameters needed, we can just call it. It got so much simpler. Before it was 2 lines, and now it's many. We have the tag in the same way that we had before. We are creating the witness using the toType tag. You can see it here. And we are doing the content. Again, in the same way that on the show function, this is irrelevant. This has no value. Like this is just unit. The compiler can erase it in principle, not right now. The same thing. If W is not used, this line can be erased, assuming some stuff. So from a runtime point of view, this should be the same as the previous code. But the main idea here is that no logic was added. This is actually the same code with the same amount of logics as before. It's just that we are like, instead of letting the compiler do stuff for us, we're doing it by hand. The good thing about whenever you can do it in a very mechanical way is that you can generate the code, okay? So this could be computer generated. Was it? No, I spent like an hour. So let's look for a second at the dream and the generated code. You can see here it's about the same. If we ignore the witness, which is TSW, and inline the stuff, it's about the same. And if we look here, again, it's about the same as this. So you may ask, why? I spent probably 10 minutes making it worse. I'm going to argue that it's simpler. We made it, we duplicated the number of lines, but it's actually simpler because you're not internalizing just one relation. You can do many types over that TI. That TI before was only useful for doing like show and maybe decode or like parse. But now you can do any computing that you want on the type level. And especially for me, I just wanted to do one thing. I wanted to do addition on the type level. And I hope you guys can just see trivially that this is just addition on the type level. I do have some demos below, but some demos on the last slide. It does work. This is just full-fledged addition. It's taking two numbers and adding them together. But keeping on the line of like, this is not harder than doing this function. It's just, more work intensive, but it's the same thing. I just spent double the time, probably more, because it's more syntax. If we were doing calc, this would just be the last function. No need for those witness, no need for like intermediary allocations and whatnot. So this is not hard. You may be still looking at me and be asking yourself, why do you want to do addition on the type level? I don't. That was just a small demo. The main thing that I want to do is dependent types. You cannot do dependent types right now in OCaml. Well, I just showed you that if you're willing to go through a very long trail, you can do it. It's really helpful, in my opinion, to look at the boilerplate version as a mechanical way. So whenever you have a code that you would like to run on the type level, you describe your code, you generate, you write the boilerplate version, and now you can see all the requirements, all the steps. You don't need to be like imagining relations, writing equations down. Trust me, I've been there. It's not exactly fun whenever you have like 30 entries and you need to see each relation and you have 5 functions. And that's one of the main problems in the traditional way that we do GADTs. For every function that you want to have like, the proofs and the behavior, we're essentially adding one parameter. At some point, if you have 5 functions that you want to behave in a certain specific way, you have like 5 parameters, and like after the third, you cannot manage it. It becomes too messy for you to manage. In general, the way that we're doing GADTs right now, it's not modular. It's like a global thing, a global definition, super weird. Should you do this? No, you shouldn't. Please don't. But you can use it as a learning step, as an intermediate step, and then later you can even arrive at the original definition by doing what we call internalizing. So you get the definition of the function that you want to define, and you just inline it together. It kind of works. The other thing that I kind of like about this is that you can write tests for your type level functions. I know that's not a problem for OCaml people because most of the time we're not doing very fancy type level functions. But I've been there, and whenever you have like a very fancy type level function, like a full-fledged interpreter maybe, it's not fun, and you cannot write tests, and if you have a bug, it's going to be like, I don't know, man, 20 files away, and like, the type would escape its sculpting. You have so many of those at some point, you just get bored. It's also like kind of fun to show like you can actually do this in OCaml. In fact, you can do formal proofs using this. Like I do have some examples of like showing commutativity of addition and whatnot, which in general is not a thing that you can do in OCaml. But remember that I mentioned that it could be computer generated. Right now it's not. to make it computer generated, we would need to have, we would need either to make the OCaml typer more powerful, and good luck on that, or we could make a PPX, but the problem is we do not have types on PPX, so that becomes messy. You can, go half the way through it and whatnot, but maybe if we had types on PPX. I'm personally not working on this right now. It's just a cool demo in my opinion. But yeah, maybe at some point we have dependent OCaml. We, using typed PPX, if anyone is interested. If anyone is interested, let me know. Here, this QR code points to the gist. So it's just a gist with examples. I highly recommend playing with it. Like try to get the dream example, write any function that you want and spend like an hour or two. It's going to be really good. I think, at least for me, it was a really good way of learning how to go each step. But yeah, that was it. Thank you so much.
Thank you, Eduardo, so much. You did a great job. And I just need to mention that this was absolutely chat presentation, just code and questions, sure, but why? Nothing more. So, any questions?
That guy.
What are some of the limitations of things that you cannot do in the type level?
Well, normal human limitations, I actually think, considering how powerful OCaml is and that it's a Turing-complete language, I think that in principle you can do anything. Like any type level computation that you want to do. In principle, you could duplicate it on the type level, index it like I showed on the slides, and just make it run. That's in principle. At some point, it gets really messy. So you need to be careful. But I think if you had a compiler, for example, that is generating the code for you, I think you could just do any program on the type level. So like, let's say you want a JSON parser. You could do it. You want to run your image manipulation tool on the type level. I think in principle you can do it.
Good.
So first remark, I'm sorry, but please don't use empty type for this example until the bug is fixed. Generally, it works much better if you have an explicit constructor, because otherwise you lose inequality information.
Can you repeat, please?
So in your example with the empty types, generally it's better to have a tag Z, because otherwise you lose inequalities, and people are very surprised when they lose equality by movie models.
Yeah. I've been there. The problem is on the LSP, it looks so much worse whenever you have the tags. So I was trying to, I personally would use. So what Dr. Florian is saying is that instead of using those empty variants here, is that you can use a polymorphic variant here and here, for example. But yeah, the problem that just for 2 slides, I was trying to make it clean so you can see the code lens and whatnot.
Well, maybe another question is that maybe a remark is also, yes, I think it's pretty nice to play with where you should internalize the type level programming and computation, because it also helps you to learn that, for instance, having clean heterogeneous list is better to have heterogeneous list with equation. Because at some point you need to choose the location when you have the type equation level.
Can you repeat, please?
So maybe my comment is that, yes, I think playing with internalizing or externalizing the type equation is a good way to find the good place to place the equation.
The good way to place the equation is
at the type level and the computation. So for instance, if you have a computation inside the heterogeneous list, my experience is that it's a pretty nice way to try to keep the equation on the element outside of the list. No, do you agree or?
I would need to see a demo. Like at least on my mind, I cannot visualize it. My bad.
Okay. Maybe
We can chat.
do the demo later, possibly.
Yeah,
Thanks.
we can chat it.
Thanks. Any? Okay.
Once you get to incomplete language on a type system, TypeScript, for example, has this turtle limit. So like at some point it stops and assumes that the type is valid. Would that be required in OCaml?
Not really. The main thing is our type system is not incomplete. I think it is, but for modules, not for GADTs. I think our car language is not. The thing here is that we are essentially telling the typer which step to do next. So if you have an infinite function, the typer is not going to try to compute the infinite function for you. You're just doing each step. Your runtime is telling, hey, do this, do that. That means the typer itself just needs to check that. It just needs to check that each step that you did is kind of valid, but it doesn't need to actually find the steps for you. That's one of the main advantages of an approach where like we do not have dependent types. By the way, this is interesting for theoretical reasons also. So like we do not have dependent types here. We're not computing the type level. It's completely decidable no infinite loop. So this is very principled, unlike, for example, in TypeScript, you can just do a trivial infinite loop, and the typer is going to guess. I don't know. Sometimes it gives you error message. Sometimes it gives you weird behavior. But, you know, TypeScript.
Cool.
Any more questions? Okay, then thank you so much one more time, Eduardo.